everyone, and a very warm welcome. You are watching the 22nd lecture in the series Mathematical Methods for Economics, and the topic for today's discussion is differentiation. Here we're going to introduce, in this video, we're going to introduce the concept of a derivative, which is nothing but a derived function, as the word derivative connotes. And also let me mention at the very outset that for the formal analysis, we will be restricting our attention to functions of one variable in this part of the series. Now, the idea of a derivative is linked to the idea of rate of change, where we look at how quickly a particular quantity changes with respect to time or with respect to some other quantity. So what we are talking about here is change. What we are emphasizing here is movement. We are bringing in change here, and this then is the introduction to you to the mathematics of change. In particular, we're going to be drawing a distinction in this lecture between what is known as an average rate of change, and we will distinguish it from what is an instantaneous rate of change, which is actually the derivative. So, but this is something which we'll be discussing later. Now, from the point of view of economics, if we think of the various applications of derivatives in economics, there are a lot of topics which where derivatives come in handy, such as when we talk of a country's growth rate, or when we want to, let's say, predict the growth in population, or we want to talk about the rate of inflation. Similarly, we may also be using the concept of the rate of change to estimate, let's say, the future demand of a commodity. There are just innumerable applications in economics, and what ties all these applications together is the fact that these ideas, they use the concept of the derivative or integrals, and basically here we are getting into a very different kind of analysis from what we've done so far. If you've noticed, if you've given a thought to the applications that I've just mentioned, there is a drift in the way we are presenting things now, and now we are bringing in aspects of movement. We are talking about change here, and this is going to be a significant shift now in the lectures to come. So, when we talk of change, according to Bronowski, in this kind of analysis, mathematics becomes a dynamic mode of thought. Bronowski was a Polish-British mathematician and philosopher, and he is associated with the BBC documentary series and the accompanying book, The Ascent of Man. So he has brought in this idea of mathematics becoming a dynamic mode of thought, which is what we are trying to emphasize here. If you notice what I've written here in brackets here, I've typed differential calculus. Now, if we just give it a little bit of thought, this is actually, the ideas the tools that we're going to be introducing in the next couple of lectures. These are formally covered in university courses, which are titled differential calculus, or if you're talking of integration, integral calculus. So that is why we are using the word calculus here. Basically, let's just think a little bit about the word calculus. Let me get into a little bit of history here, which we haven't really done in the math lectures so far, but just to deviate a little bit because this is kind of interesting. So the word calculus is derived from Latin, and it means pebble or pebbles in Latin. Basically, ancient accountants used to use pebbles for counting and for other calculations. So basically, pebbles were used for computation. And according to Binmore and Davies, calculus refers to any systematic way of working out something mathematical. So even though it was used by ancient accountants to do counting and other computation, but nowadays calculus refers to any systematic way of working out something mathematical. Now, the conception of the main ideas of differential and integral calculus are attributable to two superb minds, Isaac Newton and Leibniz. Now, I'm sure you've all heard of Newton, Sir Isaac Newton, but Leibniz is not that well known, but his contribution to mathematics, his contribution to the ideas of differential and integral calculus is tremendous. In fact, he conceived of these main ideas independently. So even though both of them, both Newton and Leibniz, were contemporaries, you can see that their work it goes back to the late 17th century. They were both contemporaries, but they developed these ideas independently of each other. And in fact, a lot of the notation that we use today for calculus, such as the d in the derivative or the integral sign, that actually came from Leibniz. And there's also this very important Leibniz rule, which you'll be doing as part of this course, maybe in the intermediate mathematical methods for economics course. So this is as far as the history of calculus goes. And now let's motivate our discussion a little bit for the formal development of the concept of the derivative. So before I get into specifics, I'll just give you a little bit of background, and basically our discussion is going to revolve around slopes here, because that is really crucial to the development of the idea of a derivative. Okay, so we'll start here with the concept of a linear function. We've already done one video on linear functions, and if you, I'm sure you would all know, or you can go back to that particular video, that if we have a linear function, please look at the slide here, if we have a linear function y equal to a times x plus b, then here the parameter a, it reflects the slope of the linear function. So this is a parameter. If you notice the way the straight line is structured, or this equation is structured, the parameter is a constant, and this is to say that the slope of the straight line is the same throughout. Now, to understand the slope, so let's just take this particular case of a straight line and illustrate. So let's suppose we have 2 points P and Q on the straight line. Then the slope of this line is given by change in y upon change in x. Basically, when we talk of the slope, this a, the parameter a, represents the slope here, and it is nothing but the change in y, the number of units by which y changes, the variable y changes per unit change in x. So the slope is given by delta y upon delta x, or change in y upon change in x, which is, as you would all know, because we are talking of a straight line here, the slope is the same, whichever point you take on the straight line, the slope is everywhere the same on a straight line. And in particular, if we take the movement from point P to Q, then we can see that we are moving delta x units in the direction of the x-axis and delta y units in the direction of the y-axis. So we have delta y being given as QR, that is the height that you have traversed when you move from P to Q, and the horizontal distance that you have traversed, delta x, is then PR. So the slope is given by QR by PR, but the main point here is that the slope is the same throughout for any point on the linear function, on a straight line. Now, let's compare this with an arbitrary curve. Let's suppose we have an arbitrary curve like the one here given in blue, which is the graph of the function f of x. So here what happens is, if you notice, this structure is very different from this shape is very different from that of a straight line, and the slope is changing everywhere. If you notice this curve, the slope is changing everywhere on this curve. For every point. So if we let's say if we think of this as some as a mound that you might be, if you think of this kind of a shape as the shape of a mound or a hill that you might be climbing, then initially the climb would be quite steep, as you can see. Then you can see that this kind of flattens off, the curve flattens off, and then again the climb would become quite steep. So what we have here is that if we were to talk of the slope, let's conceptualize how we would think of the slope of this curve at any given point. And here we're going to bring in the concept of a tangent. Okay, so what we're going to do is we're going to draw a tangent. Let's suppose we have a point P. So the first step is that at this point P, we're going to draw a tangent to the curve at the point P. The tangent here is given by L. Now, what is a tangent? How are we thinking of a tangent here? This is just to give you a little bit of a preliminary taste of what a tangent is. So here a tangent we are thinking of as nothing but a straight line which just touches the curve at the point of concern. So we are talking of a tangent at P. So we are talking of a straight line L that just touches the curve at the point P. Okay, so that is our first step in order to figure out or in order to get at the slope of the curve at the point P. Now what I'm going to do is I'm going to define the slope of the curve at the point P as the same as a slope of the tangent to this curve given by PL at the point P. And this is a natural way to think about things, because if we think of the direction in which we're going on this curve, then the direction of this curve at point P we can think of in a very natural way as the same as a gradient of this straight line which represents the tangent. So the idea that we're trying to present here is that, okay, the slope might be changing everywhere on this curve, but can we conceptualize the idea of the slope at any point on this curve? And what we are saying is that we can define the slope at any point on the curve f of x as the slope of the tangent to the curve, which is PL here, the tangent to the curve at the point P. Okay, so I hope this part makes sense. And what we are now going to do is once we equate the slope of the curve at the point P to the slope of the tangent, this then we're going to conceptualize as what is our derivative of the function at the point P, or at the point x equal to a. Okay, so the slope of the tangent to the graph at P, that is what we will call the derivative of the function at the point x equal to a. Now, just to give you a sense of what we are saying, let's take an example with another curve like this, and let's see how the slope changes. So, for example, if we look at points like P, Q, R or S on this curve, then at point P, you can see that the tangent that we've drawn to the curve at point P is negatively sloped. So here the slope is going to be negative. Whereas if we look at point Q, here the tangent becomes flat. So this is where we're going to have a zero slope, okay? Then you can see that at point R, the tangent we've drawn, which just touches the curve at point R, that is that has a positive slope. The line is upward sloping, and further, when we go to point S, the slope becomes even more positive. The line becomes steeper. So this is how we are thinking of the tangent and the slope of the curve at a given point. We are representing through the slope of the tangent, and it is the slope of the tangent to the curve which we are then calling the derivative. Basically, we're interested in the slope of the curve at a particular point, which we are representing in terms of the slope of the tangent to the curve at that point, and that slope of the tangent to the curve at that point is what we are calling the derivative of the function at that point. Now, all this is just to just motivate the discussion, and we are also going to give more formal interpretations, because see, so far we have talked of the tangent as a line which just touches the curve at a particular point where we want to take the tangent. But the question is, where did this tangent come from? So when I draw this tangent at P, at the point P, we can ask, where did this tangent come from? So what we are now going to do is, we're going to give a more formal interpretation to the concept of the tangent line, because this is something on which our discussion of the derivative is going to be based, because our formal interpretation of the concept of the derivative is then going to be based on the formal interpretation of the concept of the tangent. And let's see how the tangent then comes about. Okay, so take a look at this curve here in blue, and we have taken 2 points. Let's say we are at point P, and we move to point Q. Then the straight line that just cuts through P and Q, this straight line is called the secant. Secant is basically it's a Latin word which or it's derived from Latin, and it means cutting. So here we have a straight line which cuts through the points P and Q. It's called the secant. And what we're going to do now is, we are going to keep the point P fixed, okay? And we're going to conceptualize a tangent line now. Let's see how we get the tangent line, and this is actually quite interesting. So we're going to start bringing this point Q, because see, Q is it's an arbitrary point that I took on the curve. Now let's start bringing Q closer and closer to P. Okay, so let's see what that gives us. So now I've moved to this point R. Okay, so I move from Q to R, and do you see that the secant line now is cutting through P and R. Now let's come even closer to P. So now this is the secant, the new secant line in yellow. So basically what you see is that, as if we keep P fixed and we move from the point Q towards the point P, the secant rotates around the point P, and in the limit, do you see, as you come closer and closer to P, in the limit, the secant tends to the tangent that you get at the point P, which I've represented by PT. This is actually very important here because the slope, the slope of the tangent that we want to conceptualize a derivative, that is now going to be obtained through this kind of an analysis. Okay, so what we are arguing here is that the tangent line is nothing but this line PT, which is the limiting straight line towards which the secant tends. Okay, so we are keeping P fixed. I'll just repeat it once more so that it's clear. We're keeping the point P fixed, okay, and from an arbitrary point Q, we are getting closer and closer to P and seeing how the secant, how the subsequent secants change. So basically they rotate around P, And as you get real close to P, you can see that we're going to approach, in the limit, we're going to approach this line, which is nothing but the tangent to the curve at the point P. So this is how we conceptualize the tangent line in a more formal sense. And now we can start bringing in some math. Okay, so what I've done here is I've looked at point P and Q again, but now I've given some coordinates to it. So point P is right here with the x coordinate being a. The value of the function at point P is f of a. And let's suppose I move from point P to point Q. You can see here I've basically moved h units, okay, on the horizontal axis. So I move from x equal to a to x equal to a plus h, okay, and now if I want to look at the tangent, how do I think of the tangent now? How do I give a mathematical, how do I bring in, how do I put some mathematics into the way I've just talked about the tangent line as the subsequent secants that tend to the tangent line as Q comes closer and closer to P? Now think of this a little bit. I'll just put in the tangent here as well. So we have kept P fixed. And if I think of this point Q coming closer and closer to P, do you notice that your h becomes smaller and smaller? So if you follow the movement of my mouse, I'm coming closer and closer to P. And as I come closer and closer to P, h becomes smaller and smaller, and in the limit, h tends to 0. So it is as h tends to 0 that your secant PQ tends to the tangent to the curve, the tangent T to the curve at the point P, okay? So we are going to be relying a lot on this h tending to 0. This plays a very important role here. Okay, so now in particular, because we are interested in the slope of the tangent, and the tangent is nothing but the secant starting from PQ coming closer and closer to P, in the limit it tends to the tangent. Basically what we are trying to say here is, if you're interested in the slope of the tangent, then starting from PQ, if we get Q to come closer and closer to P as h tends to 0, that is, that will then give us the slope of the tangent, okay? Now the question is, what is the slope? Let's just back up a little bit. Let's first start with what is the slope of the secant PQ, okay, because that then leads to the tangent in the limit. So first of all, the slope of the secant PQ is again nothing but change in y upon change in x. Now, if you look at the change in y here, we have basically traversed the height f of a plus h minus f of a when we move from P to Q, right? And the change in x, the horizontal distance we've traversed, is h. So change in y upon change in x is f of a plus h minus f of a divided by h, okay? This is a slope of the secant PQ, which we also call the Newton quotient or the difference quotient or the average rate of change. So for example, if I want to understand how y changes, the rate at which y changes as x changes from a to a plus h, then the average rate of change, because if you want to look at the variation in y over a lot of values over which x changes, then the average rate of change is given by f of a plus h minus f of a divided by h. Okay. Now, what is the slope of the tangent PT? So, as I've just mentioned, the tangent PT is nothing but this secant PQ becoming, in the limit the same as the tangent, right? So, how we are conceptualizing this is that if I take the slope of the secant PQ And let h tend to 0, because automatically I will approach the tangent. So the slope of the secant PQ as h tends to 0 will then give me the slope of the tangent PT. So the slope of the tangent PT, which I am now going to call the derivative, that is nothing but the limit of delta y upon delta x, okay, or the limit of f of a plus h minus f of a divided by h as h tends to 0. So we are looking at the slope only of PQ only, the secant PQ, but we are looking at it as h tends to 0 because that is when it tends to the tangent. So the slope is for the tangent limit change delta y upon delta x as delta x tends to 0. And this then allows me to formally define the derivative, which we denote as f prime of a at the point a of the function, the derivative f prime of a of the function f at the point x equal to a in its domain is given by the limit of f of a plus h minus f of a divided by h as h tends to 0. Here we call the f function the primitive function, and the derivative is now it can be taken as what we know what is called because derivative it's a derived function. It basically that is what the word derivative connotes. So the derivative is nothing but a derived function. Alternative notation that we use for f prime of a here is dy by dx, which actually comes from Leibniz, and this then represents what we call the instantaneous rate of change. So with this we conclude the first part of the 22nd lecture. Thank you very much.